July 4, 1896, Garfield Park Velodrome, Chicago. Arthur Gardiner leaned into the wooden banking at 42 miles per hour, his front wheel inches from the rail. The crowd of 8,000 roared as he pulled ahead, entering the final lap. Then his frame tube ruptured. The welded seam along the down tube split open with a metallic crack, audible over the crowd noise. Gardiner went down hard, tumbling across splintered pine boards. Broken collarbone, fractured ribs, severe lacerations. The frame lay twisted on the track, the failed weld seam visible as a dark line where cheap forge welding had never properly fused. While American riders were crashing on welded frames and paying premium prices for European seamless tubes, a different solution was emerging in Shelby, Ohio. The 1890s bicycle craze had created 300 American manufacturers desperate for lightweight, strong tubing. Frame failures plagued the industry. Estimates suggested 12 catastrophic failures per thousand bicycles sold, with welded seams accounting for 70% of structural breakages. The welding technology of the era, forge welding and lap welding, produced inconsistent results. Stress concentrated at seam locations where slag inclusions and poor penetration created weak points. High-speed racing and rough cobblestone roads exposed these weaknesses brutally. European manufacturers offered a solution at a price. The British Mannesmann process, perfected in 1885, pierced solid steel billets to create seamless tubes without welds. The German Ehrhardt process used rotary piercing for similar results. Seamless meant no weak points, no preferential failure locations, but seamless also meant expensive. Complex machinery, specialized rolling mills, and transatlantic shipping drove costs 3 to 5 times higher than domestic welded tubes. British firms like Ackles and Pollock and Reynolds dominated the premium market, marketing seamless construction as the only safe choice for serious cyclists. American manufacturers found themselves dependent on European suppliers for quality frames, a strategic vulnerability that rankled in an era of industrial nationalism. Norman Shelby was born in 1854 in Pennsylvania, the son of a blacksmith. By age 16, he was apprenticing in Cleveland machine shops, learning precision metalwork on steam engine components. The 1870s found him working with tube manufacturing for boiler applications, fabricating pipes that carried superheated steam at 200 pounds per square inch. A trip to industrial exhibitions in Philadelphia in 1876 exposed him to European tube drawing machinery. He moved to Shelby, Ohio in 1882, drawn by rail access to Cleveland steel mills and proximity to Great Lakes shipping. In 1885, he established Shelby Steel Tube Company, initially producing boiler tubes and steam pipe for industrial customers. The fundamental problem was this: seamless tubes required expensive piercing mills that punched through solid billets. Welded tubes were cheap but weak at the seams. Shelby saw a third path: start with a welded tube, then cold draw it through progressively smaller dies. The physics were counterintuitive but sound. Cold working, drawing metal below its recrystallization temperature, work hardened the material at the molecular level. Grain structures elongated and aligned. The drawing process compressed and integrated the weld seam, forcing metal to flow and intermingle. Each pass through carbide, dies reduced diameter, refined wall thickness, and increased strength. The seam didn't disappear, but it became indistinguishable in properties from surrounding metal. In fact, the work hardening concentrated at the seam made it stronger than the parent tube. Dimensional precision was absolute. Dies controlled exact specifications to within 0.002 of an inch. The manufacturing sequence was specific: forge weld flat steel strip into tubular form, clean and anneal to relieve stresses. Draw through dies in 6 to 8 passes. Each pass brought diameter down, walls thinner, strength higher. The final product weighed less than seamless, cost 40% less, and tested stronger in every metric that mattered. By 1894, Shelby recognized the bicycle boom as opportunity. He established Shelby Cycle Company and began producing frames using drawn tubes. The marketing claim seemed impossible. Seam stronger than the tube. Dealers were skeptical. European seamless meant proven safety. Drawn tubes sounded like American cost-cutting. Shelby needed proof. He built a testing facility in the Shelby factory. Hydraulic burst tests applied internal pressure until tubes failed. Standard welded tubes ruptured at 1,800 pounds per square inch, always at the weld seam. British seamless tubes failed at 2,400 pounds with no single weak point. Shelby drawn tubes burst at 2,700 pounds and never at the original weld location. Post-failure analysis showed higher hardness readings at seam areas and finer grain structure. Bending tests confirmed it. Impact tests proved it. Fatigue testing over 50,000 load cycles demonstrated it. Shelby published results in the Wheelman magazine and engineering journals throughout 1895 and 1896. Racing provided the ultimate validation. Shelby sponsored professional riders for the 1896 and 1897 board track seasons, the highest speeds and highest stresses in cycling. European seamless frames suffered documented failures at the Newark Velodrome in June 1897 and again at Manhattan Beach in August. Shelby drawn frames recorded 0 structural failures through the entire competition season. Mechanics spread the word. Shelby frames just don't break. The turning point came at the September 1897 National Championship in Philadelphia. 4 riders suffered frame failures during elimination heats. All rode European seamless or standard welded frames. 3 Shelby-mounted riders reached the finals without mechanical issues. Post-race inspection found no stress cracks, no seam degradation, nothing. Dealer opinion shifted overnight. By 1900, Shelby Cycle was producing 12,000 frames annually, up from 800 in 1896. The company expanded from Ohio into national distribution. Racing models used the thinnest wall tubes. Tourist models offered heavier construction for comfort. Tandem frames, requiring exceptional strength for 2 riders, became a Shelby specialty, where drawn tubes excelled. The automobile industry discovered Shelby tubes by 1902. Early cars needed lightweight, strong tubing for steering columns, chassis bracing, and exhaust systems. Drawn tubes offered weight reduction versus seamless at fraction of the cost. Consistent wall thickness meant predictable performance under stress. Henry Ford's production philosophy aligned perfectly with Shelby's approach. Quality through process, not just premium materials. By 1910, Shelby steel tube was supplying Oldsmobile, Ford, and Packard with steering columns and structural components. Every tube met specification. Every tube performed identically. Mass production demanded this consistency. Then aviation emerged. The Wright brothers' 1903 Flyer used B bicycle technology, chain drives, and wire bracing. Early aircraft designers quickly needed strong, lightweight tubing for fuselage structures, engine mounts, landing gear struts, and control linkages. The strength-to-weight calculation was brutal. Every ounce mattered at altitude. Drawn tubes weighed 18% less than seamless for equivalent strength, or same weight, 23% stronger. The U.S. Army began testing drawn tubes in 1911 for experimental aircraft and artillery recoil mechanisms. European manufacturers still led in seamless production, but American drawn tube processes were catching serious attention. Shelby's manufacturing advantage became clear as demand grew. Capital investment for drawing dies cost 1/5 what rotary, piercing mills required. Changing sizes meant swapping dies, not retooling entire mill stands. Quality control was simpler. Die wear was predictable. Dimensional consistency absolute. Raw materials started as cheaper welded tube stock rather than expensive solid billets. In 1912, Shelby began vertical integration, producing their own steel strip. The Shelby, Ohio plant employed 400 workers by 1915. Technical improvements accelerated. Tungsten carbide dies replaced tool steel, lasting 50 times longer. New lubrication compounds reduced friction and improved surface finish. Multi-stand drawing equipment enabled continuous processing. By 1915, Shelby held 23 patents on tube drawing variations, die geometries, and process refinements. The company that started making bicycle frames now supplied critical components across American industry. August 1914. War erupted in Europe, and material shortages followed immediately. The British blockade cut German exports. American has industry, neutral until 1917, but supplying Allied forces, faced unprecedented demand for high-strength tubing. Military aviation exploded from dozens of aircraft in 1914 to thousands by 1918. Artillery production required recoil cylinders and breech mechanisms. Machine guns needed barrel cooling jackets. Military trucks and ambulances consumed tubing by the ton. European seamless tube production redirected entirely to domestic war needs. American manufacturers scrambled for supplies. Shelby secured Allied contracts in 1915 and 1916. When America entered the war in April 1917, production went vertical. The de Havilland DH-4, primary American combat aircraft, used Shelby-drawn tubes throughout fuselage and landing gear construction. Curtiss J N-4, Jenny trainers, built by the thousands, specified drawn tube frames. Liberty engine mounts required Shelby specifications for reliability. French 75mm field guns, manufactured under license in America, used drawn tubes in recoil systems. Browning M 1917 machine guns employed Shelby cooling jacket tubes. Production surged from 800 tons in 1914 to 14,000 tons in 1918, a 17-fold increase. The Shelby plant expanded to 3,000 workers operating 3 shifts, 24 hours daily. The performance record spoke clearly. 0 structural failures were documented in aircraft crash investigations, where drawn tubes remained intact, even when airframes were destroyed. Artillery service records showed no tube failures under sustained fire. Machine gun reliability reports cited drawn tube durability as exceptional. Some European seamless tubes developed stress cracking under combat conditions. Inferior American welded tubes that weren't drawn showed failure rates approaching 4%. Shelby drawn tubes recorded failure rates statistically insignificant, below 0.1%. The U.S. War Department's 1919 post-war analysis specifically cited drawn tube reliability as contributing factor to American aviation success. Shelby steel tube received the Army-Navy E Award for excellence in war production. International recognition followed. British and French military specifications began requiring drawn tubes for critical applications. War production ended in 1919, forcing peacetime adjustment. Shelby pivoted back to commercial markets, but emerged fundamentally transformed. The scale achieved during wartime made them a major industrial supplier. Automotive production boomed as returning soldiers bought cars. Commercial aviation emerged. Oil drilling accelerated. Construction expanded. Refrigeration became an industry. Bicycle manufacturing continued, but represented only a minor fraction of company output. The oil fields created revolution. During the 1920s and 1930s, drilling depths increased from hundreds of feet to miles. Drill stems rotated under extreme torque and pressure. Seamless tubes were expensive and available only in limited sizes. Standard welded tubes failed, under torsion, splitting at seams. Drawn tubes solved both problems. The work-hardened seam handled torsional stress that destroyed conventional welds. Cost remained reasonable, even at the massive quantities oil drilling demanded. Sizes were available that seamless mills couldn't produce economically. Texas, Oklahoma, and California oil fields adopted drawn tubing as standard. By 1935, drawn tubes dominated oil country tubular goods specifications. Average well depth jumped from 1,200 feet in 1920 to 4,200 feet by 1940. Drawn tubes made deeper drilling possible. Aircraft evolution continued the dependence. The 1920s and 1930s saw transition to all-metal construction. Drawn tubes formed fuselage longerons in Boeing, Douglas, and Martin aircraft. Engine mounts for radial and inline engines required drawn tube strength. Landing gear handled massive impact loads where failure meant death. Control surface frameworks used drawn tubes throughout. World War II aircraft. Production consumed them by millions. Each B-17 Flying Fortress contained over 200 drawn tubes. P-51 Mustangs used drawn tube structures. Production reached 300,000 military aircraft. Weight savings averaged 14 pounds per aircraft. Cost savings exceeded $80 per plane. Structural failures involving drawn tubes were statistically negligible. The jet age continued this dependence. Higher speeds meant higher impact loads on landing gear. Hydraulic systems operated at increased pressures. Drawn tubes met every demand. I'd love to hear your thoughts. Please leave a comment below and give this video a like if you enjoyed it. See you on the next one.